Now we're on to our second problem, number 3. Let me make sure it's recording. Yes. Okay, so we have f of x is equal to 3x minus 4 over x squared plus 2. Again, to remind ourselves, if we're finding a relative min and max, our process is going to be step 1 to find the critical values. Step 2, we are going to partition. Step 3, we're going to chart. If we're going to find the absolute min and max, step 1 is going to be to find the critical values, which we've already done. Step 2 is going to be to find f of the critical values, or f of the endpoints. And step 3 is to compare what you found in step 2. Again, the main thing to do is, when we're on a closed interval, make sure that when you partition and chart, you partition and chart on the closed interval. That's an easy mistake to make. So, if this is our function, step 1 is going to be to find the critical values where the derivative is 0 or undefined. So I take the derivative. This guy's form is the quotient rule. So I do low d high minus high d low over low squared. So the big, and notice I write it all out one step at a time. The derivative of 3x minus 4 is 3. The derivative of x squared plus 1 is just 2x. So now we just need to be careful and think of these as an entire piece here and an entire piece here that we're going to subtract. So now when I distribute through this 3, I get 3x squared plus 3 as one term minus 6x squared minus 8x because I distributed the 2x, and this is one whole term, right? And then I can distribute through the negative, which hits both of these and makes everything on top have the correct sign. So now when I look at it, the 3x squared and the negative 6x combine to give me negative 3x squared. The 3 comes over here, the 8x comes over here, and now I have one derivative, which makes me happy because it's nice in one term. It means in a minute when I find the derivative where it's 0 undefined, it will be quite easy. So before I do any more work, I'm going to go ahead and factor this thing nicely because I know I need to. So first I'm going to take a negative out of all these terms, and so I get negative all this. Then I'm going to use the AC method to turn this into two terms. If that's not easy for you to do, you need to look up on Google practice factoring quadratics, or please come in and we can do as many examples factoring quadratics as you need. So then the bottom just stays the same. So here's my derivative, and that's what I'm going to use when I set it equal to 0 and when I find out where that derivative is undefined. So first I say, where's the derivative equal to 0? Well, since it's a nice fraction, a derivative is equal to 0 where the numerator is 0. So that means I take the entire numerator and set it equal to 0, which again we factored. We had already factored it all the way down to this. So I set my numerator equal to 0, and I have this is equal to 0, which means either that term is 0 or this term is 0, that factor, excuse me. Either this factor is 0 or this factor is 0, which gives me x is equal to negative 3 or x is equal to 3 for possible critical values. So negative 3 is in our original interval, which went from negative 2 to 2. But this is outside of the interval. It's not in the interval negative 2 to 2, so this is not a critical value for this conversation. So now that I have my critical value, I partition. So my only critical value is at negative 1/3, but notice I want to also make sure that I include my endpoints when I am thinking of my partition. So here, remember it was negative 2 to 2, so when I set up my partition, I now have two smaller intervals from negative 2 to negative 3, negative 1/3, and negative 1/3 to 2. So notice the testing points will be only inside this interval. So it's going to be from, again, from negative 2 to negative 1/3, not including, negative 1/3 up to positive 2, including, because remember those are the endpoints. So what's a great thing in this left interval? Well, how about negative 1? So that's going to give me negative 3 plus 1, make it negative, is a negative times a negative, which is positive in this interval. Then again, if I try negative 1, this is going to end up being negative. So a positive times a negative, the bottom is always going to be positive, which is great because it's squared in this case. So we get that the derivative is negative in the first interval, which means that f is decreasing. Then I come over here and maybe I plug in 0. And so if you plug in 0 here, you get 0 plus 1, make it negative, which is negative. You take 0 minus 3, which is negative. And so negative times a negative on top is a positive. Divided by a positive, the function is positive, the derivative that is. The derivative function is positive, so the original function is increasing on that interval. Okay? So what does that mean? Well, because f prime changed sign from negative to positive, that means that there is a local minimum at x is equal to, well, what is the value in between there? How about at x is equal to negative 1/3? X is equal to negative 1/3, right? So we have our local minimum. So now we have to see our absolute extrema. So remember, to find absolute extreme values, extrema. Remember, step 1 is to find our critical values, which we've already said, just include this. And then step 2 is to find f of your critical values and f of your endpoints. So for us, it means we're going to find f of negative 1/3, we're going to find f of negative 2, and we're going to find f of 2. So when you do that, f of negative 1/3, if you plug it back into the original function, will give you negative 5 over 10 divided by 9, which is negative 9/2. If you plug in negative 2, you're going to end up getting negative 2 out. And when you plug in 2 in the original function, you're going to get 2/5. So if you take all this information together, notice this is the smallest value we have. So absolute min is y equal to negative 2/2, comma, and that occurs at x is equal to negative 1/3. Absolute maximum value, absolute max, is the biggest thing we ever get out of this function is y is equal to 2/5, and that happens, or it occurs at x is equal to 2. Okay, and that's it, kiddos. So now let's look at number 5. Same sort of dealio, yes? So if f of x is equal to x plus 2 cosine of x on the interval from negative pi to pi. Why is this interesting? Well, again, we're going to find relative mins and maxes by first, step 1 is to find the critical value, which is where derivative equals 0 or derivative undefined. Step number 2 is going to be to partition. Step number 3 is going to be to chart. Then when I want to find the absolute min and max, this is not the only way, but one way to do it is to use what's called the first derivative test, which is where we find the critical values, we take f of the critical values, f of the endpoints, actually it's the extreme value test, but whatever. Step 3 is to compare, yes? It's not really the first derivative test. The first derivative test says if it changes sign at a critical value. So we're using that in there, really, in the first one. So let's do what we got. I take the derivative, I get 1 plus, derivative cosine is negative sine, so it's 1 minus, what? 2 sine of x. So then I say, where's the derivative equal to 0? Where's the derivative undefined? Well, this is a trig function. It's defined on domain, which turns out to be everywhere for sine and cosine. They're defined everywhere. So this means that there are no critical values over here. I set this derivative equal to 0, and I get 2 sine x is equal to 1. So in other words, where is sine equal to 1/2? Well, then you remember your old buddy the hand trick, and sine is on bottom and cosine is on top. If you just want one finger on bottom for the square root of 1, then what you've done is you've really have just one finger, you have a nubbin, and then you have 1, 2 thumb, right? So that means that you get 1/2 out when you have pi over 6, yes? So that means that happens at pi over 6, right? But then let's look, it wants it from 0 to pi, so it happens at pi over 6, but it also happens over here where the reference angle is pi over 6, so that would be 5 pi over 6, because we don't go all the way over to 6 pi over 6, we stop 1 pi over 6 short. So that means inside the interval from 0 to pi, here's 0, here's pi, it's going to be at pi over 6 and at 5 pi over 6 are going to be our two critical values, yes? Okay. So then we end up looking here, and we can take our function, which is again 1 minus 2 sine x, and I want to know where is this thing positive, where is this thing negative. So our interval is from negative pi, because that's an endpoint, all the way up to pi over 6, yes? And then we go from pi over 6 to 5 pi over 6. And then we go from 5 pi over 6 all the way up to pi, because that's our other endpoint right here. Okay, so we got 3 intervals. So step 2 was to partition. Sorry if I skipped that. So here is our pi over 6. Here is our 5 pi over 6. Remember, our interval stopped over here at 0, and it stopped on this side at pi. That's why we have those 3 intervals that you see on our step 3 chart. Okay? So here is our chart, and I have got my derivative, which I want to find out if it's positive or negative, and then I end up finding what's going on there. So let's see. It turns out that if you plug in a value inside of this interval from negative pi over 6, negative pi to pi over 6, well, what's a value in there? Let's do x is equal to 0. Well, I know that the sign of 0 is 0, so this is going to be positive, which means that the derivative is positive. Let's plug in something in this interval. Well, you see that pi's in there, which is great. Again, sine is going to be, sine is going to end up being 0 in there again. So here I'm going to do x is equal to pi, which is okay because it's closed. And so we get positive, positive, which is happy, yes. Let's see. If you, is there a reason why I wouldn't like that? No, I'm okay with that. So then something in between pi over 6 and 5 pi over 6, maybe you do pi over 4, right? In between pi over 6 and 5 pi over 6, or hey, no, even one that's easier than that. How about pi over 2? So at pi over 2, sine is 1, so this is 1 minus 2, which is negative. The derivative is negative, so we get that f goes from increasing to decreasing to increasing. Right? Okay. Are we happy with that? So let's see. It's decreasing here. Let's make sure that we're happy with everything we got. Yes. So maybe I didn't like that I plugged in pi there. You can... Is it clear that if you didn't plug in pi that you'd still be happy? So maybe you plug in something else, and I think you'd still be clear that it's positive. So let's stay away from pi just to be careful, and let's think about it being from... Let's think about just maybe something very close to pi. So pi minus... Yes. So pi minus something really small, pi minus 0.1. So if you plug that in here, sine is going to be really close to 0, so that's why that's going to be positive. Hopefully that makes sense. Okay, because I think plugging in pi might be a little weird. So I've got increasing, decreasing, increasing, so that means if I have my derivative goes from positive to negative, that means we have a local what? Max at here, x is equal to pi over 6. And then we see that our function goes from decreasing to increasing. So if it goes from, derivative goes from negative to positive at x is equal to 5 pi over 6. It goes from decreasing to increasing. That is a local min at x is equal to what? 5 pi over 6. Okay. So I've got a local minimum value, a local maximum value, yes. Okay. So now let's go check some endpoints. So here's what we have to do. So remember, to find the absolute min-max, we take 1, we take our critical values, which we have, which are pi over 6 and 5 pi over 6. 2, we take f of our critical values and f of our endpoints. And then step 3 is to compare those. So f of pi over 6 is going to end up giving you, if you do f of pi over 6, remember our function is x plus, we're going into the original function, x plus 2 cosine of x. That is our original f of x, right? So that means if I do f of pi over 6, we get pi over 6 plus the square root of 3, which is going to be approximately 2.26. If you do what? F of 5 pi over 6, you're going to end up getting 5 pi over 6 minus the square root of 3, which is approximately 0.89. And then I need to do my endpoints. So I do negative pi, and I get negative pi minus 2, which is about 5.14, negative 5.14, right? I think you believe that. And then when you put in pi, you end up getting pi minus 2, which is approximately 1.14, right? So I think that we see that the absolute minimum value happens at negative pi. So this is my absolute minimum value, right? My absolute maximum value happens at pi over 6. This is my absolute maximum value. Okay. Great work. Okay. So now let's see. Now let's do some more. Let's do number 7. So 7, if our original function on number 7, let's see what 7 is. If I have the limit as x goes to 0, e to the x minus 1 over tan x, remember, recall, tangent of x, not tax, that's something else, is sine over cosine. So as this goes to 0, you know the tangent of 0 is the sine of 0 over the cosine of 0. So that's 0 over 1, which is 0, right? And you also know that e to the 0 is 1, so this thing is of the form 0 over 0, where they are both differentiable. So near that 0, so you can now apply L'Hopital's rule. So using L'Hopital's rule, you can take the limit as x goes to 0. On top you get e to the x, and then the derivative of tangent is, yes, you guessed it, secant squared. And so now when I put in 0, e to the 0 is 1, and secant squared of 0 also turns out to be 1. Why? Because secant squared of 0 is 1 over cosine squared of 0, right? But cosine at 0 is just the x-coordinate when you open up 0, so it's 1, which is 1. So this ends up giving us 1. Then we look at number 9. So number 9 is the limit as x goes to 0 of e to the 2x minus e to the negative 2x over ln of x plus 1. So we plug in, we let x go to 0, and we see that we get e to the 0 minus e to the 0, which is 1 minus 1, which is 0. So we hope the bottom also turns out to be 0. But actually, if we let it go to 0, yes, that's going to be natural log of 1, which is 0. So we get 0 over 0, which is undefined. So since both of those are nice and differentiable near 0, then L'Hopital's rule applies. So L'Hopital's rule says that we just take the derivative on the top and the derivative on the bottom. So we get 2e to the 2x plus 2e to the negative 2x all over 1 over x plus 1, which is not nice, but it works. And so now if you let x go to 0, I think on top you're going to see you have 2e to the 0 plus 2e to the 0 over 1 plus 0 plus 1. So you're going to get 2 plus 2 over 1, which today and today only is 4. Right? Now let's look at 11. So then, if we can look at number 11, you get the limit as x goes to negative infinity of x squared minus x cubed times e to the 2x. So if you let x go to negative infinity, whew, that's just ugly, right? E to the 2 negative huge is going to 1 over e to the 2 times huge, which is going to 0, right? So again, you cannot plug in negative infinity, so that's why I'm saying negative huge. So as x goes towards negative infinity, what is this piece doing? It's going 2 to the negative huge. That negative in the exponent is 1 over e to the 2 huge. But if you take 1 and divide it by a really big number, it goes to 0. So this piece is going to 0, but I think you'll see that if you put in negative infinity, that's going to go to really big huge. That's squared, so that's also going to really big huge. So this thing is going to infinity times 0. And what do we do with infinity times 0? Well, you attack the part that is 0, and you want to get this into the form, so you want to change the form to infinity divided by, infinity times infinity. So how do we get it into infinity times infinity? Well, we take this, divided by, excuse me, I need more coffee, let me have that now. So we take this, we divide by 1 over e to the 2x, because multiplying by this is the same as dividing by 1 over that. So now, if you think about it for this number 11, what we've done now is now we have it in the right form. Now it's in the form of this is infinity, and this is 1 over e to the, when you let this go negative infinity, it's going to be 2 negative huge, right? So I think the way to make this make sense and make you believe it is to write it as limit x goes to negative infinity of this over e to the negative 2x. So now it should be clear that we have it in the right form, infinity over infinity. Why? Because if you put in negative infinity and you square it, this is going to be positive infinity. If you put in negative infinity and cube it, this is also going to be a negative times a negative times a negative is negative with a negative. We've got positive infinity on top. And on the bottom, you have negative 2 times negative infinity. In other words, negative huge. This negative infinity and this negative are going to make it positive, so it's blowing up. So that means that now we can use L'Hopital's rule because the top is differentiable and the bottom is differentiable. So I take the limit as x goes to negative infinity of the top. Derivative of the top gives me this minus this. The bottom gives me this, right? So unfortunately, it's still of the form infinity over infinity. So I have to end up taking that derivative again. So when you do, you end up getting 2 minus 6x over positive 4e to the negative 2x. It's still of the form infinity over infinity because this is a ridiculous problem. And on top, so that's infinity, negative infinity. So on top you get 2 over what, negative 8e to the negative 2x. And why is that great? Because the top, this ends up going to, if you want to think about it, negative infinity. So negative 2, if you plug in negative infinity, or in other words, let it get really large, this whole thing is going to 0. Okay. All right. So then we do number 13. So we look at 13. We're so almost done. If you look at 13, if you have the limit as x goes to 1 from the right of x over x minus 1 minus 1 over ln x, as x goes to 1, this is going to 1 over 0, which is infinity, right? As x goes to 1 from the right, we have ln x memorized, and we know that as we come in this way, for ln x, as we come in towards 1 from the right, it wants to be 0 at x equals 1, so this is also going to 1 over 0, which is infinity. So this is of the indeterminate form infinity minus infinity. I don't know what that is. So I have to make it look different. So we are going to change the form by making it one term. So we do that by hitting this with x minus 1 over x minus 1, that well-chosen one. This we're going to hit with ln x over ln x. So we get x ln x minus x minus 1 over ln x x minus 1. Why is that great? Because we end up getting what? Minus x plus 1 over ln x times x minus 1. So that is now, when we go to 1, I think it's pretty clear that that's going to be of the form 0 over 0. Yes? So take a second and convince yourself of that. So now when you can now do L'Hopital's rule, because the top and the bottom are both differentiable. So L'Hopital's rule applies, and the derivative of this is first derivative of second plus second derivative of first. So this becomes this. And then the derivative of negative x plus 1 ends up just becoming what? Ends up just becoming negative 1. On the bottom, when we take some derivatives, it's going to be first. This is going to be the product rule. So it's going to be first derivative of the second plus the second times the derivative of the first, which is not nice. First derivative, second plus second derivative first, right? Okay, so that ends up giving us the limit as x goes to 1 from the right of, on top it just turns into ln x, yes, because that's 1 and that's negative 1, so it goes away. On the bottom I get ln x, what? Plus 1 minus 1 over x, because this is that and this is that, yes? So, then right now, if I plug in 1, let's see, if I plug in 1, let's see, I've got this. Oh, that should be a minus. This should be a minus. Boop. Okay, so now I think you'll see that we're still of the form 0 over 0, because again, ridiculous problem. So we take L'Hopital's rule because the top and the bottom are both differentiable. So as x goes to 1 from the right, I get 1 over x. But don't forget this 1 over, if I take derivative of the top gets me that. The derivative of ln x just becomes 1 over x. Derivative of this is 0. But you know that this is just equal to that. So when you take its derivative, this is just that. So when you take its derivative, you get this times the negative 1, x to the negative second. So you get 1 over x squared. So this is plus 1 over x squared. So now when you let x go to 1, you get 1 over 1 plus 1, which is a half. Okay, definitely it's the algebra and the being careful, which is the difficult part here. So it's the algebra, not the calculus, as always. So then we try number 15, if we're trying to find a function that does all these things. The function that does all these things, well, first I want the derivative at 0 to be 0. Well, actually it says f of 0 at 0 is 0. Okay, so f at 0 is 0. Good job. The derivative at negative 2, the derivative at negative 2, at 1, and at 9 are all 0, right? Negative 2, 1, and 9. So that means maybe down here at negative 2, who knows, maybe up here at 1. So here's x is equal to negative 2. Here's x is equal to 1. Here's x is equal to 9. The derivative is all 0, so we have some mini tangent line. I don't know if it's above or below, but for now I'll just do it like that and see if I get lucky. Then I need the limit as x goes to infinity to be 0. That means as I go out this way, it wants to settle down to 0. So that's a horizontal asymptote. We know that the limit as x goes to 6 from both sides is negative infinity. That's a vertical asymptote. So as we get closer and closer to x is equal to 6, let me make that white. So here as we get closer and closer to x equal to 6, it wants to explode down, right? So this wants to explode down, that wants to explode down. What else do you want? It says the derivative is negative from negative infinity to negative 2. So it means it's decreasing from negative infinity to negative 2. So it's going down, decreasing negative. It's also decreasing from 1 to 6, which it is. It's decreasing, makes sense. And from 9 to infinity, it's decreasing. Okay, so it's decreasing out this way, which makes sense. Check, I've done all those things. Then it wants the derivative to be positive from, what, negative 2 to 1? So from negative 2 to 1, it's increasing, which it is. So there you go, it's nice and increasing. And from 6 to 9, so from 6 to 9, it's increasing, which it is. There you go, 6 to 9, it's increasing. Check. Then it wants the second derivative to be positive from negative infinity to 0. In other words, concave up from negative infinity to 0, which the way I've drawn it, it is. So here's nice and concave up. Let me go back. Here's concave up because it holds water. All the mini tangent lines are below. It also wants it, concave up from 12. So maybe out here, it's also concave up again. And this number out here is like 12. Boop. Sorry, my pen is messing up on me. So from this point on, it's kind of concave up. That's okay. And it says it's concave down. It's concave down on 0 to 6. So on 0 to 6 it's concave down. And then also from 6 to 12 it's concave down, which is concave down from 6 to 12. And there you go. That's a picture of doing all the things that it wants to do. And then the last one is 18. So let's see what's going on with 18. So it says the figure shows the graph of the derivative of a function. So let's take a second and take a picture of it so we can all literally be on the exact same page of the book. So I see something that looks like this. What am I going to do? So it says that if this, let me crop. So if this is my derivative, what can I tell about it? So if on the exam you get the derivative of function, can you say where it's increasing and decreasing? Well, first off, I know that this thing is increasing, where the increasing is where the derivative is positive. So this thing is increasing here for these x values. So from -2 to 0. It's also increasing for these values. So for these x values, from 4 to infinity, because the first derivative is positive, right? Let's see, what else do we have? Then we also have that the function f is decreasing. Boop, boop. So the function f is decreasing where the derivative is negative. So here's the graph of the derivative, so it's below the axis here. That means for these x inputs from 0 to 4, my original function is decreasing, and that's it. So then it says, it wants us to find in part B, it says for what values of f does it have a local min or max? For local min or max, that's where, we forgot one, didn't we? Over here, the derivative is also negative. So negative infinity up to -2 is also another place where the original function f is decreasing. So then it wants to know, hey, well, let me leave it like that. So then it wants to know, hey, where do you have local mins or maxes? Here, because f prime changes sign from negative to positive at x is equal to -2, that means we have a local. Again, it's decreasing to increasing, so we have a local min. Same thing here at x is equal to 4, right? It goes from decreasing to increasing. And then here, that would be at 0, f prime changes sign from positive to negative at x is equal to 0. So since it goes from increasing to decreasing, that is a local max. I'll leave the other possible parts to you. Great work, and see you next time.